So we're going to do a little solution notes today. Sorry, this is going to be a little choppy. This is not ideal. I already have it all pre-written from previous files, so I'm just going to slide down the screen as we go, but it'll at least help you understand some of the vocabulary that we will be using as we continue on through this. So you have this document if you wanted to either download it to Notability or if you wanted to print it off. I'd encourage you to do that now and then continue the video after you're ready to go. So let's talk about a couple of these different kinds of terms, okay? So you have two different words that sound really similar to each other, but it's solvent and solute. So if you look at this picture on the right here, if we have a salt or a solid that we would put into water and then you'd stir it up, you are making a solution, okay? So it is really important for you to understand that the solvent is basically the liquid and the solute is the salt or the sugar. Okay, so if you were making Kool-Aid, the Kool-Aid mix is the solute and you're putting it in the solvent, that's the water. If you look at the definition, these definitions are not ideal because they use the other word. So you're in a constant cycle of trying to figure out what it actually means. But technical definition that we have written here is the liquid in which a solvent or a solute is dissolved to form a solution, and the solute is dissolved in the solvent. All right. The next two words are opposites. So the first one, and this is important, it's about liquids. Okay, it's when you're forming a homogeneous mixture, meaning all one mixture, which what I'm trying to get to is that is actually called a solution then when you're adding them together. So they dissolve in each other is what I'm saying. So two liquids that dissolve in each other, what we'd say is something that is a miscible liquid or miscible solution. So something like vinegar and water, those would definitely dissolve in each other. Any two liquids that dissolve in each other are miscible. Anything that does not dissolve that are liquids, they are called immiscible. So oil and water is a great example. Another one is like gasoline and water. If you've ever gone boating or fishing and you see that kind of trail off of your motor and it's almost like a little rainbow trail, that's the gasoline sitting on top of the water because it's not dissolving. So hence an oil spill, as horrible as those are, thank goodness that the oil is not soluble or it is immiscible in water, or that would be even more difficult to clean up and try to get all the oil because the oil would just dissolve in that water. Speaking of dissolving or not dissolving, something that looks like it dissolves is called a suspension. So it's a heterogeneous mixture, meaning that it's not actually all one solution, in which solute-like particles settle out of a solvent-like phase sometime after their introduction. So two great examples of that is muddy water or orange juice. So and don't even get me going about pulp, but orange juice from a distance looks like it's all one thing. But we all know that if you come back the next morning, that you will definitely see that settling out, right? So those are large particles or solute particles that are actually just being suspended in the solvent, but over time it will all settle out. So that's called a suspension. An alloy is a solution, and it's a solution usually of two metals. Alloys are really great because you can take two metals and make that new metal even stronger. It takes all the advantages usually of the two metals. So some examples are steel. That's why we can have these huge skyscrapers because of the strength. Pewter, brass are some other examples of alloys, that they're actually mixtures of other metals. All right, two other words that are similar to miscible and immiscible are soluble and insoluble. And we've actually talked about this already in our solubility rules. But if you're soluble, you dissolve. So sugar and water is a great example. Insoluble is something that does not dissolve. So like BaSO4 in water, if you would look at your solubility rules, it would say that BaSO4 is not soluble, or just a much more blunt example is a rock in water. It doesn't really dissolve, so that is insoluble. Okay, just a couple more. All right, solubility in general, I don't have an example for this, but what I underlined is what is important here. It's the maximum amount of solute that can dissolve in the solvent. So if something has a higher solubility, that means it can have more of it dissolve in let's just say the same amount of water as something else that has a lower solubility, less of it can dissolve in that same amount of water. Okay, so let's make up a random number. If 100 grams of X can dissolve while only 10 grams of Y can dissolve, then the solubility of X is much greater than Y. And there are three terms with that. And this is what you're going to work on with your worksheet. And it's actually fairly straightforward. And I'm going to do a couple examples with you right now. It's called unsaturated, saturated, or supersaturated. And I had to cut that off, and I'm sorry, but it says supersaturated. If something is saturated, let's go to the middle one. If something is saturated, it's holding the maximum amount of the solute. That you cannot have any more solute dissolve in that solvent. If you add any more, it'll usually just sit on the bottom and you can't dissolve it. If it's unsaturated, you pour a little bit of sugar or salt in water and you stir it. You could definitely put more in and it would still dissolve, so that'd be unsaturated. Then there's this really cool one that I will show a video on this later, but supersaturated. It's actually a trick. We can get things to supersaturate because the bonds and the molecules, kind of tricky to explain, but aren't lined up correctly. And because of that, you can actually dissolve more. And if you disrupt it at all, it has a really cool effect because all of it comes out and starts to solidify all at once and has a really cool effect. So let's take a look, and I know the answers are going to be here already, but I'll show you how I got those answers. So this is called a solubility curve, and this is on your worksheet. And what it basically is showing you guys, and worry less about the answers on the right here, just so we can kind of go through this, is that based on a temperature, this is showing how much of a solute can dissolve in 100 grams. So I circled the 100 grams because what I'm saying is that you got to set a certain amount that it's going to dissolve in. Because if I said it was going to dissolve in a thimble versus a bathtub, obviously you can dissolve more in the bathtub because there's more solvent. So let me just show you what these questions are referring to. So it says, how much KClO3 is saturated to, or needed to saturate 100 grams of H2O? So what you do is you go to 75 degrees, which is right here. Hopefully you can see my cursor. And I'm going to go up and find KClO3. So KClO3 is right there. So I go up 75, I hit my line, that's KClO3, and then I'm going to come across, and it's a little less than 40. So I said it's approximately 38 grams. 38 grams of my KClO3 can dissolve in 100 grams of water at 75 degrees. So you'll notice that as you change temperature, the solubility changes. Some of you might have experienced this in your life, that when you heat something up or something cools down, that maybe more or less of it can go into it. So kind of keep an eye on what that looks like. Here's another one. A solute's solubility is 55 grams per 100 grams of water at about 35 degrees. Okay, be mindful. This is the amount of solute, this is the temp. So I need 55 and I need 35. So what I'm going to do is go to 35 degrees and I'm going to go up to 55 degrees, and look at that. I'm right on the line. The line is the saturation or solubility of that salt or that compound. So that solute happens to be KNO3. So that's why I wrote KNO3. All right, next one. What mass in grams of Ki will dissolve in 100 grams of water at 10 degrees? So I go to 10 degrees, and I'm going to go up until I run into Ki. And Ki is way up here. So it's asking how much Ki can dissolve, the maximum amount, at 10 degrees. So I hit that line, it's right about here. It looks like it's just past halfway point, so it's about 137. Just a couple more here. Which solute solubility is most temperature dependent? What that means is as the temperature is going across, which one has this increasing or decreasing slope. So you can tell that KNO3 gets more severe as you increase your temperature. So that's why I wrote KNO3. All right, last two. I want to show you this math. Last one, I'm sorry. This is important. So don't just copy it down. Listen to what I'm saying. What is the minimum mass in grams of 15 grams of water needed to dissolve 25 grams of NH3? So what it's saying is if I have 25 grams of NH3, what's the least amount of water I can have and yet still dissolve the NH3? Obviously, I could have an ocean's worth. It would dissolve it. But what's the least amount? So this is what I did. Is I found out at 15 degrees, right here, this is my line, how much NH3 will dissolve. And I went straight up, look at my cursor, and it's saying 60. So look at what I have here. 60 grams dissolves in 100 grams of water. So that's my ratio now. So now what I'm going to say is, well, what if I have 25 grams of water, or sorry, of NH3? How much water will it dissolve? So this is a ratio. So I'm going to let you answer this one, but you cross multiply 25 times 100, and then you divide by 60. Okay, so this should help you out with some terms and how to do solubility curves.